Hi everyone, I'm Cody Rue. This is the Church of Logic. Today I'm going to talk about a really fun thing that I've been noodling around with and that I feel is kind of on brand. It's the Equations project. This is a project that was started by the mathematician Terry Tao, who's quite famous in general in mathematics and in particular in his field. He proved some really important open questions in mathematics, and recently he's been doing this fascinating thing, which which I really think is cool, which is basically um, try to bring people together and collaborate, massive online collaboration for like mathematical endeavors, which is inherently noble. I think trying to bring people who aren't necessarily within the inner circle of mathematics to do mathematics is kind of a noble goal. And he's interested in trying in all these new kinds of approaches to things. So we recently had these polymath projects where you took a hard problem that seemed kind of within reach, and you bring in a large group of people and you kind of brainstorm together on this kind of blog, and you try and come up with ideas and you try them out, and maybe you splinter into subgroups that try different things out. His new idea was um, similar but a little bit different. He said, "Okay, let's try and take the most boring of all mathematical structures, which is the magma. A magma is a structure that consists of a carrier set, with elements of that set, and a single binary operation, the magma operation, which I'm going to say multiplication or times, but you shouldn't think of it as actual multiplication. It is some binary operation that mashes two things together and produces an output. And that's it. There are no additional laws. Often we talk about rings or groups or operations that satisfy certain axioms, but a magma at its core doesn't satisfy any axioms a priori. You just have this multiplication. It can be anything, really any kind of operation that takes in two inputs, produces one output. So Tao was like, okay, let's take these magmas and let's try and enumerate all possible equations it could possibly satisfy. Who knows? Like, x times y equals x. That's one possible thing. Y times x equals y. That's the same one, actually. I just reversed the variable. But you could also think x times y equals y. But parenthesizing here is going to make a difference, right? Because in real multiplication or addition over the natural numbers, you can parenthesize however you want. It's not going to change the result. But in a magma in general, it is. So Tao looks at these and says, okay, well, let's take all of these kind of laws. Okay, of course there's an infinite number of them, right? You can write tons of different equations involving this operation, and you can use it as many times as you want, and you can build up this infinite number of operations. It's kind of an interesting question to wonder if you can actually build fundamentally different laws, like an infinite number of them. But a priori, yes, you can. You can write an infinite number of possible equations. He was like, okay, well, let's just take the equations that have a most four operations, four uses of that operation, that multiplication operation on each side of the equation. And it turns out there aren't that many of those. There's only 4,694, which is the number I wrote down. And so, yeah, so it's just a small number. So he says, okay, well, we can write all those down. And then we can ask, what are all the possible relationships, right? You can have a certain law and then another law, but it turns out one is more general than the other, right? Like if x times y equals y times x, right? That's commutativity. And then if you have x times y times z equals z times y times x, that's another equation, right? But the first one implies the other, right? The first one allows you to swap the order of the operations, and the second one is in particular a swapping of those operations. So the first one had better imply the second one. And he said, okay, well, sometimes it's easy to show these kinds of implications. You just, you know, do a little bit of algebra and in a couple lines you can see it. Sometimes it's harder. Sometimes it's really hard. And sometimes it's not true. Like you have you have one equation and you have another equation. It's not true that a magma that satisfies the first one also satisfies the second one. So he's like, okay, well, maybe we can figure out all the implications for all these 4,694 equations, every possible one. And you're like, okay, well, that's not so many. But it is. Um, the number of possible implications, right, is like it goes up by squares, right? And square isn't exponential, but it's still pretty fast. And so in particular, for these 4,694 equations, there's over 22 million implications here, right? And again, some of them are really easy. Probably a computer could find them. And some of them are just not that easy. They're really hard. So the question Tao asked was this: can we band together as human beings and solve all these possible implications? One problem is that how do you trust, right? You farm this out to millions of people, maybe, or thousands. Um, probably millions of people don't care about this, but a few thousands do, and this is what happened in the project. But okay, but somebody says, okay, I solved this implication. It's here, and you could say, well, I don't really trust you, right? And if 100 people come in with all these proofs, it's hard to know which ones you trust and which ones you don't trust. So you can say, okay, well, I'll only trust you if you show me that you've proven this implication. But that's also hard to do, right? Imagine this person says, okay, I've proven this implication, but it took me 1,000 steps. And that's not that crazy, right? There are a few of these equations that take hundreds at least of steps to solve. Thousands, I don't know. I'd have to look at the numbers. But there are definitely some equations where it takes hundreds of steps to prove the implication. And so now you have to stare at this proof that's hundreds of lines long, right? You have to look at each line and make sure there's not a little typo in that line. That's horrible. But Tao knows, and I know, that, hey, there are tools that know how to check these proofs. So all we have to do is ask for people to submit their proofs in this easily checkable form. And then, this component of trust becomes implicit, right? You don't have to trust people anymore because they do whatever they want to do, and then they give you this proof, and then you send it to this software, this piece of software that just checks the proof, and that says yes or no. And so I think the interesting observation here by Tao and others is that having these tools that check proofs removes the hardest, most finicky component of this decentralized mathematics. You can tackle these crazy large projects of checking, 22 million possible implications by saying, hey, work on whatever you want to work on. If you think you have a proof, you build it in this form that is machine checkable. The machine checks it, and then either it's correct, we add it to our list of known facts, or it's incorrect, and we tell you, and you go back to the drawing board. So that's what they did. That's what this project was about. And people came in, they tackled it, and they slammed it, and they solved an astronomical number of these implications very quickly, and then whittled it down to a few core, really hard to prove implications. And I'm not going to talk about too much of the specifics of these implications, but I am going to talk a little bit about some of the interesting logic and computer sciencey bits. One of them is just inspirational. All right, think about associativity and commutativity. Right? How would you try and prove that one implies the other? All right, commutativity is x times y equals y times x. Very, very simple. And associativity is this really implicit, deeply ingrained thing that says that says the grouping of the operations doesn't matter, right? That x times y times z equals x times y times z. And this one is very ingrained in us. And a natural question would be to say, hey, does one imply the other in either direction, right? Does associativity imply commutativity or vice versa? And the answer is no, neither direction holds. And a kind of interesting question is, how do you prove that an implication doesn't hold? So let me at least say how you prove that an implication holds. There's a set of rules, a set of logical rules that you can state called equational logic that is sufficient to prove all possible implications, right? It's necessary and sufficient. It's a complete logic, right? I've talked about completeness several times, and this is one of those things. Equational logic is particularly simple. It takes quantified equalities, like x times y equals y times x. That's universally for all x and y. And then it says, here are the things you're allowed to deduce using equational logic. You're allowed to deduce substitutions of x and y, for example. For example, you can say, I'm going to replace y by, z times w, right? I'm going to substitute all instances of y. You can say, okay, I'm going to apply this equation somewhere inside some other equation, right? So if I have a times b times c, I'm allowed to apply commutativity to say a times c times b, right? I'm allowed to use it inside. And then I'm allowed to chain these equalities, right? If I have a equals b and b equals c, I'm allowed to say a equals c, all right? And kind of miraculously, this plus the very basic axioms of, a equals b implies b equals a, and a equals a, which is always true. All these 4 laws together, 5 laws together, are sufficient. All of those laws together allow you to prove all the equational things that you want to prove, right? So at the very least, you can say, okay, if I want to prove an implication, I just apply these laws all over the place and try and see what happens. Okay, but that doesn't really help you say I can't prove something, right? Because it's, you apply these rules, you deduce things. Who knows whether you can apply further rule and get the equality you finally wanted or not. In general, this is a case of undecidability, right? This is one of the cases, I'm talking about this equational logic. It's less general than full first order logic, but it's still general enough to have this phenomenon of undecidability, where there are some implications that are just really hard to prove or disprove. So in general, it's undecidable to take in, 2 equations and know if one implies the other. But in practice, we know how to do this pretty well, right? We know how to build tools that prove these implications. One of them is called Vampire, and I love that name, and it proves many of these implications. Another one is called Otter, but in general, there are many tools. Well, there are several tools out there that are very good at these kinds of implications, and people have used them extensively in this project to prove, tens or hundreds of thousands of implications. Okay, but that doesn't help disprove, right? So the first way you might disprove an implication is say, hey, what if there is a law? What if there is a structure, a given specific structure, like the integers, that satisfies one of these equations? If I interpret, the magma multiplication in a certain way, and doesn't satisfy the other, well, that certainly means that the implications shouldn't, because by soundness of the equational logic, right? By the fact that equational logic really means the real implication in mathematics, you know that if the implication holds and the first equation holds, then the second equation would have to hold as well, right? So if you can find a specific structure where the first one holds and the second one doesn't hold, that means there can't possibly be an implication, right? So for associativity and commutativity, you just have to prove, say, associativity doesn't imply commutativity by finding an operation, a magma out there, and an operation on that magma, such that associativity holds but commutativity doesn't hold. And that's actually pretty easy if you know anything about mathematics. You just find an operation where the order, the association of the operations, right? What How you group them doesn't matter, right? And one of those is, say, the symmetries of the square. If you take a square and you label the corners with A, B, C, D, the symmetries of the square, so reflecting over the two axes or rotating the square, right? That forms a group. And in particular, those operations can be chained. And the grouping by which you do those operations doesn't matter. That seems almost trivial, but it's a real fact, right? You can either do a symmetry flip and then two rotations, or a symmetry flip and a rotation and then a second rotation, and that doesn't matter, right? They're operations you do in a certain sequence, but you can do two of them at the same time, and that's okay, right? But symmetries of the square are not commutative, and that's kind of a cool little exercise I want you to do at home. You can see that rotating and reflecting and rotating aren't the same operation. They're different operations. And if they were the same operation, then symmetries of the square would be commutative, but they're not. And so this is a disproof of that first implication. You could imagine that maybe symmetry, x times y equals y times x, implies associativity. So the other direction, you would have to find a counterexample there. And I don't know if I want to give this one away. I would let you think about it. Think about it. Think if there's an operation that you can think of that is symmetric, right? The order the order of the operands doesn't matter, but is not associative. So the grouping does matter. There is a simple such operation, and computer scientists should know this one. So I'm not going to give away more than that. All right. So in this project, people have looked for tons of these counterexamples. What's kind of cool is there are some implications where some of these counterexamples have to be infinite. Every finite such potential counterexample can't actually work. You have to go into the infinite. So this is kind of cool. There are only a few of these implications, but you can see that automated methods might struggle with these because, well, you have to build an infinite counterexample, right? Computers aren't good with infinite things. Another technique that can actually deal with this infinity is uses implicitly kind of the completeness of equational logic. So one kind of cool thing about equational logic is that if you can't use these 5 equational rules to prove something, then the implication must not hold. And there's actually an even more clever way to use completeness of this sort, and that is, imagine you orient the rules from left to right, or from right to left. All right, so instead of an equation, you have a computation in some sense, right? So instead of like x times y equals x being your equation that you're trying to reason about, you could say, oh, x times y reduces to x, right? So instead of being, an equation that you can apply in either direction, you say, okay, if I see an x times y, I'm allowed to replace it with an x, but not vice versa. I'm not allowed to take an x and then somehow magic up a y and replace it with x times y. So if you have these orientations of rules, and you have 2 further properties, all right? The 2 further properties are this, or 3, I guess, further properties. The first property is all these rules should be should be the same as the equations you started with, right? The rule should subsume the equation, or rather the opposite. Like the rule, if it was turned into an equation, it would satisfy the original equation, all right? And the second property is all these rules taken together, if you reduce willy-nilly, you eventually get to a form that can't be reduced further, right? X times y reduces to x has this property, right? It's called termination, and basically you can only reduce it a finite number of times, right? Because you see that the thing gets smaller and smaller, right? And eventually it's going to reach some smallest possible, atomic form. And the third property is a little more subtle. It says that the order of applications of rules doesn't matter, right? So if you have x times y equals x, right, you can see that, x times y times z is eventually going to reduce to also x, right? X times y times z, the inside reduces to x, so you have x times z, and then again reduce it, that goes to x. But you could imagine x times y times z times w, right? And there are two paths, right? You can reduce the left hand first, the x times y goes to x, and then you have x times, z times w, and that further reduces to x. Or you do the right hand side first, x times y times z, and then that further reduces to x times y, and then that further reduces to x. Okay, this property, where the order in which you do the rewrites, the position at which you do the rewrites in the order, doesn't matter, is called confluence, right? If you have this departure, eventually things will conflue back into a single point. If you have these two properties, confluence and termination, then you have this fascinating phenomenon, which is basically to determine whether an equation holds, you apply the rules to the left and the right until you get these normal forms. And then you just compare the normal forms to see if they're exactly identical, if they're the same. The property says if they are exactly the same, then yes, the original equality holds. But if they're not, then the original equality cannot hold, right? So the idea here is to take an equation, turn it into a bunch of rewrite rules, maybe more than one. And hopefully those rewrite rules have these properties. They are contained in the equation, they're all implied by the equation, they are terminating, and they are confluent. And if you have those three properties, then you can just apply them computationally to your target equation and know whether that equation holds or not, assuming the original equation, right? This is a little bit complicated, but this is a standard technique, and it's a very powerful one because it doesn't care about finiteness of models, right? It only cares about whether you found this special rewrite system. And there's a huge body of work to do this automatically as well. So now computers are back in the game. They know how to prove these non-implications between complex equations. So, all right, I just want you to get excited about the equations project and about how we know how to prove reason about equations, computationally. One other thing I wanted to note, yes, there's this algebraic structure in mathematics called a Boolean algebra. Now, generally, we think about Boolean algebra as zeros and ones, and the and or operation on them. But there's this second operation called a NAND, right? And basically, a NAND is an and then followed by a negation. And what's kind of cool is that you can get all the other operations back out of a NAND. And there are Boolean algebras that have more than two elements, right? There are Boolean operations that have four elements, Boolean algebras, right? They have four elements, etc. There are even infinite ones. It's kind of a cool structure that has been studied for a long time. What's kind of crazy is that there is a way to write axioms for these Boolean algebras, right? So instead of saying, oh, it's the and operation and the or operation, or the NAND operation, you can just say it is an operation that satisfies all these equations. And what's funny is that the NAND can be characterized by a single axiom. There's a single equation you can write such that if a structure satisfies that equation, then that operation is, or that structure is a Boolean algebra, and that operation is the NAND on that Boolean algebra, which I think is crazy, right? And it's a single operation, it's a single equation. And it appears in this list of 4,694. Does it? No, actually it doesn't. I'm sorry. And all right, so I just wanted to talk about this and get people excited about this stuff. Maybe I'll talk about it more if people express interest. And yeah, feel free to check it out. I'll post some links, in the in the description. And until I see you next time, take care.